That's right. Can everybody hear me okay? Is the microphone working? All right. Excellent. I'm glad there's so many people turning up to talk about a topic that's really kind of fascinated me for the past, I guess, 2 years right now. Full disclosure, I was actually supposed to give this talk at last year's csvconf, but had difficulties getting to Mexico. It was easier for me to get to Italy from San Diego than to get to Mexico, so I'll let you wonder about that mystery on a different time. But the thing I wanted to talk about today is not really a particular topic or expertise or anything like that. It's more of a way of approaching data, which is really kind of my area of interest in methodology and everything. So the title of my talk is Connecting with Graph Neural Networks from Zero to Slightly More Than Zero. Just a show of hands, how many of you have heard, at least heard of graph neural networks before? Show of hands. A couple. Out of you, how many have actually used them in any capacity? Okay, well, so you're all kind of in the same boat as me. I'm very new to this area myself, and so if you don't know anything at all about them, you will officially know a little bit more once you walk away from this talk. And then if you do know a little bit about them, hopefully you'll know more that you walked in with, not less. Again, my name is Grant. We're not going to really talk too much about who I am, even though I made a whole section about that, because honestly, who really cares? We have a short amount of time anyway. If you do want to know more about me, I'll be around both days of the conference, so just come up and find me. So yeah, getting into graph neural networks, probably most of you have heard of neural networks as just sort of a general class of algorithms that is used for anything from prediction to classification to regression. Any kind of traditional machine learning problem is open to deep neural networks in their own sort of right. So I guess the first question I would ask, or I should be answering, I suppose, is aren't there already lessons for this? Aren't there plenty of lessons for if you want to learn about graph neural networks, you can just go and learn them on your own time. You don't have to be here for me. My answer to that is that when I tried to do it that way, I found a lot of the resources were not really beginner friendly. They always had sort of these presumptions of expertise coming into them that I didn't really feel like were really representative of kind of the beginner mindset. So I wanted to make something that's a little bit more friendly, and this 15-minute sort of format hopefully will be able to prove whether or not I'm able to do that. So there are quite a few lessons out there already, and we'll get into this sort of talk as well. Before I get into this any further, I'll just show you a little, I made all of this sort of presentation in a application called Obsidian, which is itself a graph-based sort of note-taking algorithm, or sorry, application. So hopefully it'll be a little bit more topical if I approach it in this way. So we're just going to get into what I find wrong with the current materials that are already out there. A lot of them are so involved. Yeah. A little bit bigger. I can zoom in, I believe, or well, let me just close the graph view and then see if here we go. I don't know how to zoom in with Teams. There we go. How about that? All right. All right. So I'll go with this. A lot of the sort of tutorials and how-tos and introductions to graph neural networks don't even bother to necessarily tell you what a graph is, which is something you probably want to know if you don't use them in your day-to-day work. It is usually done given examples of data sets, and that is already sort of pre-prepared for the problem, which is typical of all sort of machine learning tutorials and lessons in general. But it's particularly problematic when you might want to use GNNs for your own kind of problem, because you don't know how to get your data from that step to where they're applicable to GNNs. And then a lot of the introductions I found are very heavy on the mathematical notation. Here's an example I found just on the free code camp introduction to graph neural networks. This appears less than a quarter of the way into the lesson, and this is considered one of the easier equations on that page. I'm not a particular kind of person who can intuit what equations like this mean, so I really don't like it when a lot of the introductory materials, as they're called, go in this way. There are a few exceptions that I note here, both of them coming from the now defunct publication distill.pub. I highly recommend you go check them out if you are interested in going in deeper than I can get in 15 minutes. I found both of these very good. The first one is called A Gentle Introduction to Graph Neural Networks from Distill. The second one is Understanding Convolutions on Graphs, and they're actually both parts of a two-part series on that website. They're very good. They have interactive material, not just sort of static presentations, so I highly encourage people who are interested in graph neural networks to check these out. Let's start with, just going into the basic question of what is a graph and how do you make one. Probably all of you have seen some illustration like this in a textbook if you've ever taken a class related to mathematics or something like that. The basic elements of a graph are pretty simple. You have the entire graph, which I label as G. Some of the tutorials out there call the entire graph U. for reasons that I don't fully understand. So I will leave that problem to you to decide. And the other pieces of a graph that you need are the vertices, also called the nodes, and then the edges, which are basically the connections between nodes, that could sometimes called edges or links. And every one of these pieces of data has its own kind of value. So typically, if you were to break this out into a table, you might have a table for the nodes and all of their information, and then another table for all of the edges and their information. That's one of the reasons I find these graphs kind of more intuitive when talking about certain kinds of data than just sort of flat tables or what we call tabular data. So it's really nice to be able to sort of a really nice intuitive way to represent things. Naturally, the flavor of the connections between these elements can come in sort of two different flavors. One is directed, where there's basically a source and a destination node, and then there's undirected, where you can just kind of have an arbitrary connection that can go either way between the nodes in your graph. And that's really kind of the basics of what you need to know about graphs before we get into how I use them. One of the potential issues of the graphs, and one of the reasons that people don't use them as often as they do, is that for any single graph, there are multiple equivalent ways that you can represent them. So here I have a simple 4-node graph with a very sort of circular connection between them. And below that, you'll see different tables, different matrices, as we like to call them in mathematical context. All of these are equivalent ways to represent the same graph. So the question whenever you're using a graph representation is like, how do you decide which representation is right, because your algorithm may function differently on each of these matrices, what we call adjacency matrices, based on the connections in the nodes. So that's one of the big decision points that makes it hard to know when you can jump into using a graph for your problem. So that's just what I want to explain why you maybe don't see these more often. So, but you do need to transform your graphs into one of these representations, because otherwise most of the algorithms you have prepared don't really work that well. So because a lot of the tools you'll work with will probably expect like tensors or matrices or some kind of tabular data. So unfortunately, we do kind of have to find a flat representation for a graph, even if it's not necessarily the most intuitive way to represent these things. What a graph neural networks then? So now that we know what a graph is, we can get to what is called the original paper for graph neural networks, was published just about 20 years ago in 2005 by Gori, Monfardini, and Garcelli in Italy. They are all at the University of Siena, or at least they were at the time. And they sort of introduced this concept of how you could use graphs for a neural network kind of representation. This is literally the picture I have here is the first figure in that paper, showing how you represent a house as a graph in a basic way. So you basically have, from what I understand of the paper anyway, you would have nodes representing the windows, the door, roof pieces, walls, and all of that. So you basically decompose the house into its different components and link them together based on how they are actually working together in a house. And this is sort of the introductory example they give for bringing graphs to a new audience. You know, a little bit of a stretch for me, because it's still not intuitive to me to think of a house as a graph, but we'll go with it for now. One concept that's related to graph neural networks that some of you may have heard of in other sort of contexts is convolutional networks. So just very, very briefly, for those of you who don't know what convolutional neural networks are, they're a way of processing data in neural networks that takes advantage of the fact that some pieces of data are immediately next to each other. The intuitive example being images or video, because what you do is your algorithm basically runs over not just each individual pixel on its own, but groups and collections of the pixels that are immediately next to each other. So you basically take a square or some kind of filter and sort of slide it over your image, which has sort of these different representations. Let me go to this slide right here, which may help make that a bit more intuitive. So on the left here, you have zoom out slightly. Is on the left there you have an image, basically break it out into a grid. Each pixel has its own position, and then you can break it out even further into the red, blue, and green channels. You basically go over each of these images and slide back up now. You know, basically think of them as linked in the way that's on the right-hand side here. So each individual position becomes its own node in the graph. They are all linked sort of side by side to each other. So convolutional networks are basically, you can think of it as a specialized case of graph neural networks, what's really different about graph neural networks in general is that you can break out of what you can sort of make your own definition of what adjacency means in the convolutional image processing sort of setup. Adjacency is defined simply spatially, so whatever pixels are next to each other, those are considered adjacent. But if you want to back out a bit further, you can define adjacency in whatever form makes sense for your domain, whether it's in a social context or a social science context, physics, whatever it is your problem domain is, and just define adjacency based on what makes sense for you. I'll skip over here with current neural networks is just to say that they're also related to how you can process text as well. And then, so yeah, basically that's just a high level view of like what we're actually doing when we're creating a graph neural network. Is we take this concept of adjacency in the network and break it out to generally be appropriate to our domain. So let's say we're working in kind of a social media kind of domain. You could have each node represent a different user and different edges represent the relationship between those users and that kind of thing. You could also take a different formulation, say an entire graph represents a single user and do different kinds of classification that way. It's just a really flexible format that lets you decide what is the most appropriate way to represent your information. How do they work? Very simply, I have a simple sort of 5-node network here. Let me zoom in a bit more on this. You have a simple 5-node network here on the graph. And then in a GNN, the simplest way to sort of make use of them is to slide down here. Basically, you perform an aggregation or what we call pooling. So whenever you want to create new information about a node, the simple way to do that is you follow the connections to that node, basically take their representations, whatever they may be, and then you aggregate them in some sort of fashion. The aggregation can be just summing them together. You can be taking the average, you can be taking the maximum, any kind of mathematical function that sort of breaks it down. You do that for every single node and every single edge in your graph. And then out at the other end of the GNN layer, you end up with basically the same graph, but it's a new representation of it based on the information that is from its neighbors in the graph. And if you do that multiple times in a row, you basically impute information about a given node based on its nth degree sort of neighbors. So after one layer, you're incorporating information from its immediate neighbors. After a second layer, you're incorporating information from its second degree neighbors and third degree neighbors and so on for each new layer that you add to the network. And that's really the sort of magic behind graph neural networks is this thing called message passing. So yeah, basically broken into 3 steps. You just gather all the information about your neighbors that are relevant here, aggregate it by whatever aggregation function you want to use, and then you pool it through some kind of update function. Usually that's a choice of the user on the end. So you just sort of figure out what way that you can sort of transform your data and put in as many layers to your network as you really kind of like to end up with a new and interesting sort of representation of your graph, even though it's actually the same graph. The difference is how you're encoding it. So just to sort of round out my time, since we're coming up here, is like, what can you do with all these kind of graphs? What are some unique applications to doing this? One of the cool ones that I found is sort of biomolecule prediction. So molecules and a lot of biological constructs in general are quite intuitively represented as graphs. So there are a lot of applications for GNNs to say, predict the toxicity of a molecule or predict what the aroma might be, predict if it's going to explode when I shake it and other kinds of things that you don't want to test empirically. So it's a way to use graphs for a biology domain. In security, which is relevant to some of my work experience, they're really important for like fraud detection. So you can have different nodes in your graph represent people who are related to the person you're trying to determine is committing fraud. So you can incorporate lots of different modalities of data, from demographic information to relationship information to past transaction information. It just makes it very easy to combine lots of different types of information that you wouldn't normally see in the same table. And that leads to some very high performing fraud detection algorithms and other security applications. And then finally, there's maybe something that's a bit more relevant to some of the topics that have been talked about here at csvconf this year. You could do things like disease detection for people or for crops by representing your data as though this is sort of the most intuitive image I can find from this example. You're basically turning a field of crops into a graph based on parts of an image, and then you can train an algorithm basically to spot based on an image taken by any kind of camera really to determine whether or not there's a disease spreading along the crops or identify where the disease started, so on and so forth. So there's so GNNs, to summarize everything, are a very, very versatile algorithm to use for many kinds of prediction algorithms, and they're sometimes a lot more intuitive than different ways of tabularizing your data for that kind of purpose, even though you can use those as well. So I think GNNs are kind of underhyped compared to LLMs or some of the other exciting sort of AI advances out there. So I really wanted to bring them to your attention and hope maybe you can brainstorm ways that they may apply to your work as well. So I'll end there and switch over to questions. Apologies if I can't hear you and here. The acoustics are not really to my liking, but I'll try my best to hear what anybody's saying. So thank you for staying. I'm really thrilled you all stayed around here. And yeah, let's talk more about graphs.
Chen.
So this is good. So in your abstract, you mentioned that you just recently got into GNNs, and as somebody who wants to get into this, do you have to have terabytes of data to do anything
Not
useful?
terabytes. No, I don't think so. You can actually get by with very little data. Many of the example like tutorials use, I would say, relatively small data sets. So even then they can be quite powerful. And you can even get started in something free to use like Google Colab and other sorts of tools. So you definitely don't need a whole big data infrastructure with billions of records or anything to make use of these kinds of algorithms. They're very intuitive and very flexible with like how much data you have.
Great, thank you.
Any other questions?
Thanks for the introduction to this. I'm still trying to wrap my hand around it. So it seems to me, and I'm really just asking, like this may be a way to deal with one of the issues of network analysis, which is generally you can have one set of relations per node, right? So is one of the use cases here that you could take multiple relationships and be able to sort of neural network them, whereas within network analysis you can't really show that, or am I totally missing the point?
No, I think you're right on track. Definitely social media analytics and anything you can think of as a network is very well suited to things like graph neural networks. Definitely the more types and more, what's the right word? The higher the number of edges that you have for the example that you want to use, the better they'll generally perform, because as I was mentioning, one of the rich features of graph neural networks is they transform your original graph based on the number of connections that it has. So the more layers you have of that kind, the richer and newer and kind of insightful embedding you can get. So yeah, that use case is a textbook example of what you'd want to use this kind of algorithm for. I really think it'd work out well.
Anyone else?
So you talked a little bit about these other forms of neural networks, convolutional and recurrent neural networks. Is the way to sort of think about the decision about which of these models to apply, to kind of think about the dynamics of the structure of the system itself? Like how are the objects within this system related to one another, and then kind of apply a model based upon that, and then apply whatever machine learning you want to that? I'm trying to understand, I guess, the types of problems that we would apply this type of technology to versus some other.
Yeah, the types of problems are definitely very versatile, like I mentioned, because for any problem you could think of, there probably is a way to apply graph neural networks to them. And one of the things I didn't have time to get into are the different types of graph neural networks out there, because there's more than one flavor of them. Convolutional networks, like I mentioned, kind of this natural affinity for video and image, just based on the way that they work and their original sort of neuroscientific inspirations. So I wouldn't try to think of like what are the limits of whether or not I can apply this. I would say if you have a way, however simple or however basic it is, that you can represent what you're interested in as a graph, you'll be able to find a flavor of graph neural networks that applies to it. It's just a matter of like figuring out what types of relationships actually make sense, because one of the nice things about these is how multimodal that you can be with your data. You can have many different types of data that aren't necessarily easy to integrate in a simple table or even naturally come together. That's one of the flexibilities of having a graph representation, and therefore having a type of neural network that can process that kind of information. So Don't know if that's a definitive answer to your question, but long and short answer is that there's probably, for any problem you can think of, there's a variety of GNNs out there that is has a niche for that problem.
Great, thanks.